Yay, matrices! I'm sure you remember all of linear algebra, since it's awesome. But just to make sure you remember, this is how you multiply them. Inside the computer, the memory is in the form of one long array going one row at a time. So in our first matrix, the computer would have A, B, C, D, E, F, G, H, I. And then outside of that, say that it's a 3 by 3 matrix. A fun thing we can do when calculating these is by using multiple processes or threads. Say we have the first process working on the top 2 rows of the first matrix. Then this process will be looking at all of the second matrix for its calculations and ending up filling in the top half for the product. The second process will do the same thing, but replacing the top with the bottom. You could also have more processes or split the second or split both. Now I can just hear you questioning which one is best. This shows an instance of how long it takes to multiply 2 1024 by 1024 matrices given some variables. The colors represent the difference between how many processors are used. This test was run on a machine that only has 2 cores. This is why the ratio difference from 1 to 2 is generally more significant than going from 2 to 4. Another factor to consider is the ordering of the 3 nested loops to accomplish matrix multiplication. Mathematically, the amount of work being done is equivalent in every case. However, because of locality, the order in which we place these loops matters. Going across matrices by rows is far better spatial locality, because that is the order in which they are stored in memory. This is the same chart colored differently to better visualize a different factor. Each color represents a different permutation of the 3 loops used to accomplish this multiplication. As you can see, this ordering makes significant changes in runtime.
You didn't think you were rid of me, did you? Now we get to talk about Y8664. It's similar, but with fewer options. Every program really only does a few simple things. It moves data around, does simple operations, moves through the code, and sets condition flags. Ultimately, that's all you need.
But why would you limit yourself like that? Why would anyone do that to themselves?
Because I'm much smaller and faster than you. Let's get rid of a register and the carry flag. We don't really need those. For each step of executing code, I will fetch the next instruction, decode the instruction, actually do the instruction, interact with memory, and then do it again. While not an exhaustive list, these are some commands that I still support. The C moves are conditional moves. They're like jumps, except there's no jumping, so I guess not that much like jumps.
Do those new symbols look familiar to anyone else? Anyway, we have changed all the symbols again. These are from Digital Logic Design. It's a course we have yet to go through, however we are expected to know all of it now. On a hardware level, there are only OR, NOT, and AND gates. That's okay though, because we can easily make the rest out of these. You can even do more complicated stuff like open parentheses S and not, open parentheses, T and R and not, open parentheses P or Q, close parentheses, or open parentheses not, open parentheses T or P or Q, close parentheses, or open parentheses P and Q and R, close parentheses, or open parentheses P, and not, open parentheses Q, or R, close parentheses, close parentheses, close parentheses, close parentheses, or open parentheses Q, and not, open parentheses P, or R, or S, close parentheses, or open parentheses T, and not, open parentheses P, or R, or S, close parentheses, close parentheses. I don't know why you would want that specifically, but a girl can dream of such things. And of course, there are many setups that would accomplish this same outcome. Please like and subscribe, and maybe one day our dreams will come true of more gates and more logic.